Hi everyone, in this recording we're going to discuss some general graph visualization strategies. We'll focus especially on node link and adjacency matrix views. So first, how can we use the ggraph package? So ggraph is like ggplot2 but for graph structures. So instead of taking a data frame, you pass it in a table graph object. And once you give it the table graph object, you can compose a variety of layers. Each layer is going to correspond to some visual mark. So here's an example. This is the high school dataset. It's the same one from the very first lecture on tidygraph. And I'm just drawing a node link diagram. So this is the table graph object. Edge link is drawing all the links. Node point is going to draw all the points on top of those links. It's doing all the graph layout so that the points are organized behind the scenes. Okay. This kind of key idea is that we're able to compose many different layers on top of one another. It's not just like a general purpose single function. Instead, it's just like ggplot. We can compose in however order we want. Maybe we could put different layers on top of here. You can also do things like customize the theme or add a different scale. Okay. So that's just showing the node locations. We can also encode different attributes of the nodes and the edges. So that is done using the AES command, just like in ordinary ggplot2. So in this example, I've calculated something called log degree, which is just I look at the size of each neighborhood for each node, just that's the degree, the number of neighbors it has. And then I've taken the log because some of them have many more neighbors than others. Okay. Then I've encoded that degree as color and size. So in this case, you see these nodes with very few neighbors. This one only has 2 neighbors. It's going to be a lot smaller and a lot darker. Those nodes, those are the high school students with many friends, are going to be lighter color and larger. You can do the exact same sort of thing with edges. You would just put an AES inside of geom edge link instead of node point. Okay, so that's using ggraph. How do we do these sort of visualizations in D3? So the first thing is it's often useful to write the data as a JSON object rather than a CSV. So CSV works if you have flat data where you have many separate rows, but there's no kind of larger hierarchical organization. JSON is useful when you are trying to structure into several groups. So what I've done here is I've gotten one data frame for just the nodes, and I've gotten another data frame for just the edges in 1957. I've taken those 2 data frames and I've combined them into a single list. Now, when I write this to JSON, I'm going to have a kind of nested object where the first key gives all the edges, that's one data frame, and then the second key gives all the nodes. It's a separate array of objects, one array element per each row. So this is just really nice because instead of having to give 2 CSVs to D3, I can just give it one JSON object and it will read in all the data. Okay, so that's how you read it in. Once you have the data, how do you actually get the layout? How do you show where to append circles on the screen? A very common paradigm for working with node link diagrams is to use something called a force-directed simulation. So let's just look at some example code, right? This is taking the node and link information out of that JSON object that I just defined. Once I define those nodes and links, I pass the nodes into force simulation here. This is from the very root of my simulation. And what it's going to do is it's going to start running a kind of physical simulation where each of the particles in the simulation corresponds to one node. So here each particle is one student. And I have some rules saying how the particles interact with one another. So here it's saying this link force says, using the links dataset, if 2 particles are connected by a link, try to pull them together. There's a force that attracts them. But then otherwise, there's a kind of force that repels every other node from one another. So there's this kind of counterbalance between connected nodes being pulled together and all other nodes, or just nodes in generally, being pushed apart. And this is going to make it so that the tightly connected nodes are going to be forming little clusters, and then if they're not connected, they're not going to be overlapping. these other forces, so this is just saying start my simulation at the center of the screen. I think the canvas is 600 by 600. And this is saying run the simulation for 100 time steps. Okay. Now the really important part is that when you run a simulation, it's going to actually modify the nodes and the links in place. So even though at the beginning I don't have any pixel coordinate information in my node or link objects, after having run the simulation, I now have attributes within both of those arrays which give then the x and y locations for each node and the endpoints of the links. So once it has those x and y locations, right, these are the x and y locations that are created by simulation, I can use that to do the general update pattern and append nodes and lines to the screen. So here I've drawn all the nodes as circles. The locations are coming from the simulation. Here are the links. Each link object has a source and a target. So these are the two endpoints. And the source has an x and y pixel coordinate. The target also has an x and y pixel coordinate. And a line in D3, or in just SVG in general, is just a line that connects two endpoints, x1, y1, x2, y2. So that looks like this. This is what it looked like after having run for 100 time units. It makes sense that these two clusters, or these two components, are separated from one another because since there are no links to tie them together, they are kind of repelling one another. And these things which are really tightly connected, they're going to be pulled together because there's a force that's pulling them together. So that is showing after having run the simulation for 100 time units, right? Like I ran setup simulation and this ran it for 100 time units. But you can actually continue to visualize the simulation as it's running, right? So what I've done here is I define a little function that's all it's going to do is it's going to look at whatever the current value in the nodes and links data arrays are, and it's going to reposition the circles and lines according to the updated positions, right? So you imagine that the x and y pixel coordinates are being changed because the forces are interacting with one another physically, and it's going to move all the circles and lines. And this is just selecting all those circles and changing the attributes to reflect the simulation results. Right. Once you have that function, calling simulation.onTick and then that function is going to say for every iteration of that simulation, redraw the visualization. So that's going to look like this. Okay, I'm going to refresh the screen so that we can see what it looked like as it was running. Okay, did you see that? So it started off kind of in the center of the screen, and then they're repelling one another, and eventually it kind of stabilizes because there's a kind of temperature parameter in the simulation that cools it down so that it tries to kind of stabilize the locations of all the points. So at this point, there's no interaction, but you can add interaction by using something called d3.drag. So you usually will want to have something called a drag start and a dragged function whenever you use d3.drag. Drag start is something that is going to run every time the user clicks on a node. So I just said that it kind of cools down and stabilizes. Usually, if the person's interacting with it, you kind of want to heat it up again so that things start moving around. If it cooled down and the user is clicking on it and you don't heat it up, then you might move that one node, but nothing else will move because it's all already frozen in place. So here, it got heat up by using this is this alpha target parameter. Right. And then the other thing that you'll want is you want to change all the forces according to how the user is dragging things around, right? So if the user moves really fast, you want to say kind of that particle now should have that force moving in however the user is moving things. Right. So once you've defined those two functions, here's the start and here's this dragged, the modifying the two forces, the x and the y force. Now, anytime I click and drag, it's going to move stuff. Oh, okay, these circles are too small. Yeah, so, okay, you get these forces and you can play around. It's a pretty common way of visualizing these networks. It's kind of fun. People get impressed with the movement. I'm actually not totally convinced that just adding this sort of dragging interactivity is really that useful. But at least if you ever see this in practice, you'll know how it's being done. Okay, so that's all about node link diagrams, both using ggraph and R and using D3 through simulations. But there are going to be a lot of networks where node links just don't make that much sense, right? So here's the kind of canonical example. There are just too many nodes and way too many links, so that you try doing this sort of force-directed layout and you just get a big hairball, right? Not that useful. So what can you do instead? Perhaps the most common thing to do is to draw an adjacency matrix. So the idea of an adjacency matrix is to kind of put all the nodes along both the rows and the columns, and then if there's a link between kind of node I and node j, you go to that coordinate, the ijth coordinate of this big matrix, and you put kind of a black square there. That means that they're connected. Or if you have different types of edges, you can have the different types of edges be different colors. So we'll see an example of that in a minute. So here is an example of just the high school data set again. Or no, actually, no, I'm not. Yeah, I think this is the high school data set. I'm not sure. But the syntax is going to be the same for every single data set. The way it works is G is this table graph object. I'm saying the layout is a matrix, which is not the default. The default is going to be a node link layout, which is why in the previous ggraph I didn't have to specify anything here. When I say matrix, it's saying, okay, use an adjacency matrix layout. Now I can add on layers. The edge tile is what's drawing these black squares. Right? So the edges are being encoded by tiles rather than lines. Chordifix is saying I want little squares rather than rectangles, which would happen if you make the height different from the width. And these are just adding labels for what does each row correspond to, what does each column correspond to. Okay, so relatively simple syntax for a ggraph. How do we do this in D3? The basic idea is that you have a data set, an array, where each array element corresponds to one edge. Right? And then at that point, once you have one array per edge, you just append a different rectangle for each of those edge elements. Right? So we've seen SVG rectangles already. This is all it's doing, right? It's taking that array of all the connections, all the black squares here, and then it's entering them, it's appending those rectangles, and it's setting attributes of the rectangles. Now this is the tricky part. You need to know what x value, what y value associated with each of those rectangles. Right? But you can do that just using a scale. Right? So in this case, x is a scale band. Scale band because you need to map these discrete IDs to some continuous location on the screen. I'm using the same exact scale for both x and y because they're mapping the same things, right? They're both mapping from a set of node IDs to some continuous representation, and one is just basically flipping it on the side. The width and height I can get from the bandwidth. That's just going to be the space between two neighboring IDs. And fill here is, I actually have an edge type in this data set. So we're going to be seeing some edge types here. And fill is just a color scale. So it's saying from the different edge types, use a different colored rectangle for each. Right? So this is exactly what that output looks like. Right? Here's it's the Le Miserable data set. The colors are the kind of connection, and then I have every single character here. Right? So this character, and you have, right, all the colors are saying the type of character that that person is linking to. You can see the little clusters. So these are characters who interact a lot with one another. Here's another group of characters that interacts with one another. You can see that there are some characters who interact with many people. There are others which are more sparse, so they don't interact with as many people. Okay. Now there's a subtlety always have to pay attention to when you're using an adjacency matrix visualization, is that it really depends on the order of the nodes, right? The reason there's some nice structure visible here is because the nodes are sorted in a way that the clustered nodes are all next to each other. So if you were doing this by hand every time, that would be kind of complicated. But fortunately, there's this nice package. You can click the link here. It does a lot of different kinds of reordering algorithms for adjacency matrices. So to make the one above, what I did is I imported the reorder library. So if you go to the HTML for the source for this example, you can see that I import this reorder.js library. And that gives me something called reorder.graph. Once I have that, I can get my node data, I can get my link data, and then that defines a kind of graph object within JavaScript. And then I can call any of a variety of ordering functions on my graph. Right? So here I'm using spectral ordering. It doesn't really matter what ordering you do, as long as the nodes in a similar neighborhood are going to be placed next to each other. Okay, so the main reason you would use an adjacency matrix is that when you have a very dense network, using the node link representation, you're going to get lots of overlapping edges. And that can be very hard to read. But in an adjacency matrix, it's, even relatively small tiles, we're still able to notice some real pattern. Right? So you can actually visualize some pretty dense and large networks using adjacency matrices. Right? The biggest downside with this kind of visualization is if you want to do any kind of topological query that's outside of just the neighbor, it gets very hard, right? If I wanted to say something like, find all the neighbors who are 2 steps away from Valjean, right? You could find the immediate neighbors very easily, but then to find the second order neighbors, I need to figure out who is this rectangle, right? So I'd have to go all the way down for this rectangle and get someone, right? And then I'd have to look up that character, right? And then find their neighbors, right? So it gets a really kind of tedious calculation in adjacency matrices compared to in a node link, you can just follow the path by 2 hops, right? So, neither of these is going to be uniformly better. There are a lot of proposals out there that try to do some sort of hybrid between, both having some adjacency information and some link information. But these are a little bit more complex. We'll start reviewing these next week.